The title is Privacy Preserving Computer Vision Through Optics Learning. Can you hear me well, right?
Yes, we hear you well.
Okay, thank you. It's a little bit of noisy around, so okay. So yeah, so nowadays, as you know, we have cameras everywhere, and we would like to use them with the smart computer vision models to assist us in our activities, right? However, we need to ensure that this system protects our privacy. So, for example, we would like to use this model, for example, in operating room to assist doctors. But of course, we will like to preserve the privacy of the patients. This is just one example. You can also have this. You want to have cameras, for example, in your house to monitor maybe your grandfather or grandmother, and maybe, but you don't want to maybe uh, like you want to protect their privacy. So yeah, in general, the privacy issues in computer vision pipeline arise after the image acquisition, right? Because cameras are designed to acquire high resolution images. So this make easy to identify sensitive information like faces. So if an adversary get access to the videos, he could identify sensitive attributes and objects like faces, nudity, credit cards, etc. However, there are some computer vision tasks that don't need a high quality image or video. For example, in action recognition, we resize the video and we use a convolutional neural network to extract the global features and predict the action. So in this case, we don't really need like high resolution images. So there are some software level solutions which consist of applying some operations after image acquisition, like for example, blurring, pixelation, or uncompression. However, this operation usually decrease the computer vision task performance. So one question here is, how can we preserve the privacy before or during image acquisition? So let me briefly mention how the image formation model in the cameras works. So given an object, the light emitted or reflected by this object is represented by a complex field, which consists of both amplitude and phase information. As this field travels through the space, it reaches the lens. And then once reaching the lens, the light wave is influenced by two factors. The aperture function, which represents the size and shape of the lens, and the phase modulation, which describe how the lens bends or modify the light. Together, these two factors determine how the field is transformed as passed through the lens. So the light continues to propagate to a distance, let's say D2, and the image is formed in the image plane. So as you can see, the image formation directly depends on the phase profile, what that we then denote here as a phi, which describe how the lens surface modify the light. So a traditional surface profile with a spherical lens, like the traditional cameras, they can be approximated by this equation, the left side equation, and it depends on the radius and curvature R of the lens. On the other hand, we can parameterize this phase profile phi using Zernike polynomials. So these Zernike polynomials represent wavefront aberrations, and the combination of this polynomial with different coefficients generates the surface profile. So you may wonder, what is this wavefront aberration? So for example, this wavefront aberration that the name is horizontal tilt, it basically represents an inclination on the front wave in the x direction. Sorry. The other one, for example, this vertical tilt represents the inclination on the wavefront in the y direction. And for example, this one, this Zernike polynomial represent the focus of the camera. So it's similar to how the lens move forward or backward to focus. So as you can see, this there are other ones like atismatines and so on. So they basically represent like these wavefront aberrations, and we can parameterize or we can design a camera basically by combining these wavefront aberrations. So we basically learn how we combine these coefficients, these Zernike polynomials. So usually the cameras that we know, the commercial one, they are designed to minimize this aberration in the lens, right? Because we don't want we want the camera to acquire images very like high resolution images with that they looks with high quality images. So they are designing to minimize the aberrations. So in this research, we rely on the converse approach. We basically want to maximize the aberration in the lens to obtain a highly degraded image and provide privacy protection, visual privacy protection. However, now the question is, how can we distort the image while obtaining good performance in computer vision tasks? So this is our proposed general framework. We want to minimize the loss associated with the task, and we add this loss here that basically aims to maximize the difference between the input and the measurement and what the camera acquires. So we have implemented our privacy preserving approach in 4 computer vision tasks. In all of them, we employ our proposed privacy preserving camera and propose different learning strategies. So the first work was on human pose estimation, and this was an oral presentation on ICCB 2021. So in general, this is our method with the proposed camera here, which is basically our encoder, and the decoder, which is composed here of the decoder is composed of a backbone and a human pose estimation network. So for the human pose estimation, we adopt the open pose network. This network is basically composed of a backbone and a set of convolutional layers that detects the key points and their relationship. In this work, we don't train the open pose network from scratch, but instead we use the pre-trained model and fine-tune some layers. And also we split the output features into the body and face parts, and only use the body features in our optimization. So our optimization problem combines two goals. The first, to visually distort the image while still performing human pose estimation with high accuracy. So these are the two goals. The one is to distort the image, and the second one is to try to preserve the human pose estimation accuracy. The result of the training process is the camera lens, the parameters of the camera lens is what we optimize. The coefficients that we combine, the coefficients when we combine the Zernike polynomials and the parameters of the pose estimation network. So here you can visualize the optimization process where we where face recognition and image quality decrease while our network still estimates a human pose. So we train our proposed approach end-to-end on the COCO dataset, and also to evaluate human pose estimation, we use the object keypoint similarity metric, and we adopt the standard average precision and recall scores. And we use an implementation of the arc face network to perform the face recognition and measure also privacy. So here are some results. In the first row, we show the result of the traditional non-privacy preserving pose estimation network without considering the face key point as our upper bound. So now we can show the results when using the focus lens and low resolution cameras. And as you can observe in both approaches, in the focus and low resolution, the image quality decrease, but also the human pose estimation decrease. And finally, in our proposed optimization approach, our proposed optimized lens here, we basically decrease the image quality, and also we preserve the human pose estimation performance as much as we can. So these are some qualitative results. So you can see here the original video. This is the result using the focus lens. This is the results using a low resolution, and here we have the results using our designing lens. So our second work was in human action recognition. So here we propose an adversarial framework to learn the distortion and perform human action recognition. For both computer vision tasks, we implement a proof of concept system in my previous lab in Colombia, and we use it to test our privacy preserving method in images and videos acquired with this camera. So the framework is similar to the human pose estimation one, but here we include an adversarial network that basically aims to predict if the privacy preserved image has some visible features or attributes. So basically, it's composed on two or three parts. First, the optical layer. Maybe I can have first the optical layer. Second, the action recognition network, and third, the adversarial network. So we use a pre-trained action recognition network like Rubik's net and the standard cross entropy loss. Also, to avoid losing temporal information due to the spatial distortion, we propose to use temporal similarity matrices. And specifically, we build temporal similarity matrices from the original and private videos, and then we compare their structure using the mean square error. So for the adversarial network, we define the adversarial attack as a multi-level binary classification problem. So specifically, each video frame has one or more private attributes, including like skin color, face, gender, nudity, and relationship. So therefore, we train a neural network that takes a private video as input, the frames of the video, and tries to identify the corresponding private attributes. So our objective is to decrease the performance of this network using our private video frames. So this is the general algorithm. Like for each epoch and every batch, we first acquire the private video with our optical layer. Then we update the parameters of this optical layer, the action recognition network, and the adversarial network. And we update each set of parameters individually after freezing the others. In our experiments, we use multiple data sets and metrics. We use the HMDB 51 dataset for action recognition and report the standard average classification accuracy as metric. On the other hand, to perform privacy validation, we did experiment on the face recognition. So we measure also image quality and test the adversarial network performance. In the blue boxes, sorry. Okay, so in this figure showed the trade-off between the privacy protection and action recognition on the HMDB dataset. So the red dashed line indicates where action recognition accuracy is equal to adversarial network accuracy, and the horizontal dash purple line indicates action recognition accuracy on the non-privacy videos. And then the results show far in this direction are better. And here we show the performance obtained by low resolution cameras. This is the focus camera. And recent work proposed in reference 3, and finally our method outperforms the other as it's far from the others in this direction. So here are some simulation results from our method. The second row shows the original videos of the HMDB51 without privacy protection, and the last column shows a failure case example. So much time. Okay, so now let's continue maybe with I will skip the image captioning and go to the last one. So yeah, maybe I can go quickly on image captioning. So basically here we also try this task on image captioning. We basically fine-tune a ResNet, and we employ an LSTM to generate the caption. Here we use a similar approach. So we basically learn the optics, and at the same time we learn the parameters of the ResNet pusher structure and also the LSTM. And we use similar metrics, like we measure low resolution image quality, and we also measure the performance on the image captioning generation. As you can see, we basically we try to reduce the image quality, but the model is still able to learn what is happening in the image. And finally, this is our last work. That it was a CPR paper last year. So this is an approach for face dye identification. So this is basically done in two stages. The first one is to optimize the camera optics and the heatmap regression network. So the heat map allow us to infer a global geometry information from the source image, like, for example, head pose, the position of the eyes, the nose, and mouth, without exposing the subject or the person identity. And in the second stage, our primary goal is to learn the parameters of a conditional GAN, that basically this GAN generates a new face identity using the input, only the input privacy preserving image like this, and the heat map. And then we can generate, with a reference image, we generate a new one. So yeah, for the stage one, we basically optimize the camera lens parameter, similar as previous approaches. And basically here the task is to generate this heat map. And then in the second stage, we freeze the lens and also the regression, the heat map regression network. And then we learn the conditional GAN that generates a new image using a reference image. So we'll skip these details. And yeah, so we basically use different data sets and matrix to validate our approach. We measure the distance between the generated image and the original image. We also measure the detection of the face and also the detection of face landmarks in the private image, and the FID to see if the method generate the generated images generalize well. So okay, I will skip this. And finally, all of these four words have been developed a proof of concept optical system in our lab. So to further validate this, we built this proof of concept. So this is a general setup where there are two cameras here. One camera is basically to capture the image without privacy, and the other camera is to capture the image with privacy. And here is the deformable mirror. This device, this optical device, basically simulate or emulate the lens. So we first simulate the lens in software, like the results that I showed you before. With this, we learn the Zernike coefficient, and then we load the learned coefficients in the deformable mirror and calibrate the point spread function in the camera. So as you can see here, okay, here is the setup. We acquire the videos. As you can see, we have the two cameras, one camera that acquires the video with privacy and the second one without privacy, just for having a ground truth. So here are some results. This is for action recognition, for the action recognition work. So here, yeah, you can see some examples. And this is, of course, there are some failure cases. So yeah, basically, for the takes away, our key idea is that we can modify the camera lens to sorry, to distort or degrade the image in such a way that the identity of the subject is obscure, but we still preserve important features for computer vision tasks. Of course, there are specific computer vision tasks that we can use for this, like action recognition. For action recognition, for example, we don't specifically need high quality videos to do the task. to do the computer vision task. The second takeaway is that the camera lens can be parameterized using the Zernike polynomials. So we learn our privacy preserving lens by basically adding aberrations. It's like the opposite of traditional cameras, that in traditional camera you basically want to remove these aberrations. And the third takeaway is that there is a trade-off between image degradation and computer vision task accuracy, as you can see maybe in the results. Of course, if we decrease the quality of the image, then the computer vision task accuracy will also decrease. This is basically because of in all of this work we use pre-trained models, and these pre-trained models were pre-trained on high quality images. So there will be also there will be always a trade-off between this degradation and the task if we follow the same approach I have done in these works. And finally, during inference, we can deploy our system in hardware by implementing the lens in the camera or as a software solution only. Here I show you a prototype that we built in the lab, but these lens can actually be printed and you can basically put in a camera and use it. So finally, a special thanks to my co-authors. I did most of this work when I did an internship in Stanford. And now I just to finalize in some minutes, just to say that now I'm moving more towards working on safety in general. Actually, last week we had the one workshop on safety. This one, the Safe, Trustworthy, Multimodal AI System. And we had a lot of attendance, and also 51 was also a sponsor. And yeah, in this QR code, you can check the website. I will upload the recordings. We have great speakers like Joshua Benjo, Florian Tramer, and Jarin Gal. And in KAUST, where I'm working in KAUST as postdoctoral researcher, we are building here a strong research group in AI with Professor Bernard Gannon. So we have several open positions for postdoc research scientists and PhD students. So if you are interested, you can fill out this form or contact me on LinkedIn or email.